You type cat sat on the and an AI finishes your sentence. It feels like magic, but under the hood, it's just numbers flowing through layers. Today, we open a real language model and watch 4 words travel through every single stage. Most explainers wave their hands. We won't. We'll use the actual smallest real model, Qwen 0.5b, and a tool called Torch Info to see the real layers, the real shapes, the real numbers. No magic, just machinery. So how does a language model actually think? Let's follow one sentence all the way to the prediction. Meet our specimen, Qwen 2.5, the half-billion version. About 494 million numbers arranged into 24 repeating layers. Small enough to open up on a laptop, real enough to be honest. And this is Torch Info. Point it at the model and it prints a map. Every layer, what shape goes in, what shape comes out. This map is our whole itinerary for the next 10 minutes. Here's the whole journey on one page. Text becomes tokens, tokens become numbers, numbers become meaning vectors. They flow through the transformer stack and out the other side comes a prediction. We'll walk every step. Stage 1. Text input. Our sentence is cat sat on the. To you and me, that's 4 words. To the model, it's meaningless. A computer can't do math on letters. So the first job is simply turn this text into numbers. Stage 2. Tokenization. A tokenizer chops the text into tokens, common chunks the model knows. Our sentence splits into 4. Cat, then space sat, space on, space the. Notice the spaces ride along, attached to each word. Why chunks and not letters or whole words? Letters are too tiny to carry meaning. Whole words would need millions of entries and still choke on new ones. Subword chunks are the sweet spot. Qwen's vocabulary holds 151,936 of them. Stage 3. Token IDs. Every token is just a row number in that vocabulary. Cat is row 26801. Space sat is 13177. On is 389. The is 279. Our sentence is now 4 numbers. Stage 4. Word embeddings. The real layer is embedding 151,936 by 896. Each ID looks up its row, a list of 896 numbers called a vector. So 4 IDs become 4 vectors. Shape 1 by 4 becomes 1 by 4 by 896. There's no clever math here. It's literally a giant lookup table. 151,936 rows, each 896 numbers wide. The ID just picks the row. The magic is that these numbers were learned during training. So why 896 numbers per word? Because together they place each word in a vast map of meaning. Words that mean similar things land close together. Cat near kitten, far from car. This is where language becomes geometry. Stage 5. Position. Here's a problem. Right now the model just has a bag of 4 word vectors with no sense of order. Cat sat and sat cat would look identical. For language, order is everything. The fix is a neat trick called rope, rotary position embedding. It rotates each token's vector by an angle set by its position. The first token turns a little, the fourth turns more. Position becomes a rotation. Why rotate? Because then the angle between any 2 tokens encodes how far apart they are. The model can literally feel These two words are 3 steps apart. Order, baked in as geometry, no extra numbers needed. Stage 6, the transformer block. This is the engine and it repeats 24 times. One block has 4 moves. Normalize, pay attention, then normalize again and think. And after each of the 2 big steps, it adds the result back in. Let's open one up. First move, RMS norm. Before doing anything, it rescales the vector so its numbers are a consistent, tidy size. Not too big, not too small. Same shape in, same shape out. It's the quiet step that keeps everything stable. Now the star of the show, self-attention. Each token gets to look at the other tokens and pull in context. Our the looks back at cat and sat to figure out what it's referring to. This is how words share information. How does it decide? Each token builds 3 vectors. A query, what am I looking for? A key, what do I offer? And a value, what I'll hand over. Mash the queries against the keys and you get attention weights. Here it is in miniature. The scores each word. Cat 0.5, sat 0.3, on and the a little each. Those weights blend the values together into one new context-aware vector for the. Shape never changes. Next move, the feed-forward network. Now each token is processed on its own, pushed up into a much wider space of 4,864 numbers, passed through a simple switch called SILU, then squeezed back to 896. It's the model's room to think. And the glue that holds it together, the residual connection. After attention and after the feed forward, the model simply adds the result back onto what went in. It never throws the original away. It only adds refinements. Stage 7, repeat. That whole block, norm, attention, norm, feed forward, is stacked 24 times. Torch info literally lists decoder layer 0 through 23, every one the same shape in, same shape out. Each pass sharpens the meaning a little more. Why so many? Because depth builds understanding. The early layers catch grammar and simple patterns. The deeper ones catch meaning and relationships. Our 4 vectors go in as just words and come out as words that understand the sentence. Stage 8, one last normalization. After all 24 blocks, a final RMS norm tidies the numbers one more time to get them ready for the prediction step. Same familiar shape, 1 by 4 by 896. Stage 9, the LM head. A single layer that turns each token's 896 number vector into a score for every word in the vocabulary. 896 numbers in, 151,936 out. One score per possible next token. But we only care about one position. The last token, the. It's the one whose job is to predict what comes next. So from the 4 rows of scores, we keep just the final one. Stage 10, the logits. Out comes a wall of 151,936 raw scores. One for every token the model could say next. Higher means more likely. Ground scores about 13.8, floor 13.0, table 12.5, while nonsense like banana sits far lower. These are raw, not yet probabilities. Stage 11, softmax. It turns those raw scores into probabilities that add up to 100%. Bigger scores get a bigger slice, and it exaggerates the leader. Now the numbers are something we can actually read. With real probabilities in hand, the model can either always take the top one, safe and predictable, or roll the dice among the top few for a bit of creativity. That single choice is the difference between a boring model and a lively one. Stage 12, the prediction. For cat sat on the real model's top pick is ground at about 10%, followed by floor, grass, and table. The cat sat on the ground. From 4 numbers to a sensible next word. And to write a whole sentence, just append that word and run the entire pipeline again, one token at a time. The ground, then the next word, then the next. That loop running blazingly fast is exactly how ChatGPT writes. So here it is, the entire journey on one screen. Cat sat on the becomes tokens, then IDs, then vectors. It flows through 24 transformer blocks, gets normalized, scored across the whole vocabulary, softmaxed into probabilities, and out comes ground. Strip away the jargon and it's simple. Look up each word, add its order, then let attention and thinking repeat 24 times. Score every possible next word, turn scores into odds, and pick. No magic, just a very deep, very well tuned pattern machine. That's a whole language model, one sentence deep, small enough to open, and now, hopefully, no longer a black box. Thanks for watching.